welcome everybody. And today we have this presentation by Giovanni. And the topic today is about heterogeneous graph. And this is the fourth session in this second part of our tutorial on advanced aspects of PyTorch Geometric. And so Giovanni, please go ahead and for the other one, enjoy the presentation.
Okay, so welcome everybody. Today we're going to talk about some other developments that happened in the version 2 of the PyTorch Geometric library, which is how to handle heterogeneous graph data. So let's start by defining what an heterogeneous graph is. So far we have talked mostly about homogeneous graphs. Homogeneous graphs are graphs in which the nodes of the graph belong to one single type, and also the edges connecting the nodes belong to one single type. So for instance, if we think about a social network, the only node type is the people, and the connections is the friendship. Or for instance, if you think about web pages, the link is the edge in the graph, and the web page is the type of node, the only type of node. Whereas when we are dealing with heterogeneous graphs, the things gets more complicated because we have maybe more than one node type and different kind of edges connecting these nodes. So here on the right, you can see an example of how an heterogeneous graph might look like. If we bring it down to pieces, we can see that, for instance, the circles represents authors in this domain. The hexagons represent papers. And these are the two type of nodes that we have in our graph. Then we might have different links between them. So for instance, the dotted link is indicating a co-authorship, so it will link only two author node, whereas one solid arrow, one solid link means that an author has written a certain paper, whereas the dashed line is a connection between the two entities paper, meaning that one paper cites another one. So as we have seen so far in the homogeneous graph representation, we can store the nodes into a matrix, and we can use another matrix to represent the edges. However, here it's a little bit more complicated because we cannot have one single matrix or table to represent all the nodes, because maybe nodes might have different dimensionality, and so we cannot use the very same homogeneous representation for this type of graphs. In this case, in PyTorch Geometric, the Heterodata class comes to our aid. The Heterodata class is the equivalent of the data class for the homogeneous graphs, but it has some differences with respect to it. For instance, so here you can read the description. I will not read it for you, but I would just want to focus on some parts, which is the fact that in the heterogeneous data representation, we have disjunct storage objects. What does it mean? That we will have a different representation for the different types of nodes and edges in the graph. And how are they stored inside of the heterogeneous data class? They are basically nested Python dictionaries. So later in the notebook we will see it properly. But let's start thinking about the way to store heterogeneous graphs as nested Python dictionaries. How do we construct a heterogeneous graph in PyTorch Geometric? So we have seen that we have a specific class, which is Heterodata class, but then we need to impute the values of our graph. So For instance, if I want to instantiate the representation of the nodes for the type of node paper, there are usually three ways that I can do it. So by declaring the data object and then adding the information in the square parentheses, and for each square parenthesis in which we specify the type of the node that we are dealing with, we can also specify some let's say values that represent this type of nodes. So for instance, in this case, we have data paper.x. X is going to be the matrix storing the features of our nodes, but we can also have other other variables. So we might have the class, which is which will be data paper.y or something like this. So there are three ways, as I said, to initialize this data, which is the first one we have already seen it. The second one is to actually use the type of the node that we want to represent as the name of the variable in the form of the class, and passing a dictionaries containing all the matrices related to that particular type of node. Or we can simply pass to the class a nested dictionary, as in this case. Basically, the same goes for when we want to store the information for the edges. However, edges, as we have seen, usually involve three type of identifiers, which is the type, the source type of the node, the actual type of the edge, and the type of the destination node. In this case, for instance, if we want to instantiate the values for the edges, we have to use this representation. And again, we can use the three different ways that I told you before, although there are some changes here. Because since we need these three identifiers, we cannot simply write them down into a single string. So in the first case, we have the types separated by a comma, whereas in the second type, we need to use this double slash separator in order to actually identify that type of edge. Or in the third way, we need to pass as key of the dictionary a tuple of strings. Again, this heterodata is very useful to store also type of nodes that have different dimensionalities. So for instance, we might have the author node, which has, I don't know, a feature dimension of 8, and the paper node, which has a feature dimension of 16. And in this way, we can actually do that, which is something that we could not do with the homogeneous representation of the graph, so with the data class for homogeneous graphs. So there is a little bit more of a specification that I want to do, which is once you have instantiated the values for each type of node or for each type of edge, then you might access all the specific attributes of for each type of element by simply using this formulation here. So basically, your data dot the attribute for which you want to extract information underscore dict. And if I do it for the example before, I will get basically the two matrices, the X matrices for the nodes and for the edges. Okay. Why do we need this kind of representation? Because later we're going to need it when we pass the information in input to the model. We will use this specific representation. There are also some properties and utilities that I want to discuss a little bit about, which is the how we interact with the basically with the data type. So here it's a list of properties that I've extracted from. There are many more in the documentation, but so let's say that if you want to store all the information contained in the variable, you can just store the property store, which returns a list of base storage objects. You can do it also only for the nodes or for the edges. And of course, you can also retrieve the list of node types and edge types. Since the data is represented as a nested dictionary, you can also get in output the entire dictionary using toDict function. And also there are some utils that you can use to, let's say, analyze the content of your heterogeneous graph. For instance, if it has some nodes which are isolated, or if the nodes have self-loops, if it is directed or undirected. Let me just put a note here, which is how do we say, for instance, that a node has self-loops? A node in an heterogeneous graph has self-loops if for each edge type there is one edge that basically loop over one node. So remember that when we talk about heterogeneous graph, we need this for each edge type and not for the only one as in the homogeneous version. The same goes, for instance, if the graph is undirected. So a graph is undirected if for each edge type we have a connection back and forth between a pair of nodes. I think these are the two most useful things, properties of the data object, which is how we extract the metadata, which is a representation of all the types that you have inside of your object. It will output a list of node types and a list of edge types. And then there is this other function which allows you to convert a heterogeneous graph into a homogeneous one. How does it do it? Well, because basically it will take all the elements, all the nodes basically, and will merge into one single representation. Now, I will not go into much detail about this, but let's say that if you have, for instance, two type of nodes and they have the same feature dimensionalities, they will be put together into one single matrix representation. It will be slightly different if you have different dimensionalities for the two types. However, you can still represent a heterogeneous graph as a homogeneous graph, performing some transformations, of course. Another set of tools that are already that we have already seen also in our tutorial, which is how we transform the data before the model process it, which is the suite of functions given by basically PyTorch .transformation package. I wouldn't say all, but the documentation says that most of the transformations that you can apply to homogeneous graphs, you can also apply them to heterogeneous graphs. I have some examples here. So as I told you before, if I want to add, if I want to convert the heterogeneous graph to an undirected heterogeneous graph, I can use the first transformation here. Or if I want to add self-loops. And there are some other transformations that, however, work exactly as for the homogeneous case. So for instance, in the normalized feature example, you will have all the dimensions of the feature normalized to sum up to 1. And of course, you can also apply other kind of transformations like the random node split, which will produce a training, validation, and test split. However, it will do it only for the types for which there is a target specified. Now that we have talked about how we represent heterogeneous data, how do we process this heterogeneous data? In PyTorch, we have two ways to construct heterogeneous graph neural networks, which is firstly, in premise, you can use a homogeneous graph neural network and convert it to a heterogeneous one, or you can implement directly a heterogeneous type of graph neural network. I will here, what I want to show you is how you can take a homogeneous graph neural network and convert it to a heterogeneous one. So let's suppose you have a graph neural network described as in the picture. So you have these two sage convolutions, and that's basically it. You have these two simple sage convolutions. The way we can convert this homogeneous graph into a heterogeneous one is to use this function, which is toHetero, in which you pass the model that you want to convert, the metadata of the data upon which this model will be applied, and the type of aggregation that will be used inside the different models. I will tell you what it means in a while. So basically, what does this produce? This will produce a new representation of your model in which you have a graph neural network that will parse, that will take in input nodes coming from each edge type. So basically, an edge type, we have said that we have the source and the destination. When we convert a homogeneous model to a heterogeneous one, we will have a graph neural network parsing the nodes the nodes related to a specific edge type. It's a little bit more of an explanation here. So you might have seen that here we have a strange initialization of the input channels, which is basically we do not specify how, what is the dimensionality of the input feature. To actually perform the transformation from homogeneous to heterogeneous, we have to use this lazy initialization. What does it mean? That basically the first time we are going to give an input the data to the model, it will automatically calculate the dimension of the input features and apply that value to the initialization of the convolution. Why is it needed? Because as I told you before, we're going to have a representation in which we have several different convolutions for each edge type. In order for each edge type to work with different type of nodes, you need to have different input dimensions. In order to not hard encode these input dimensions into the model, you can use this lazy initialization. Alternatively, you can also construct your own heterogeneous graph convolutions by simply extending the class HGTCon. When we go from a homogeneous model to a heterogeneous one, we might have a schema like this. So as I told you before, here we have these two sage convolutions for the different iterations in the convolution process. These convolutions are basically duplicated in order to be able to work with a different edge type. And it does it for each edge type and for each step of the convolution process. Okay, so let's have a look at some piece of code. So in this example, I have created a very simple heterogeneous graph in which we have two node types, which is authors and papers, and we have two type of links between them. So write and cite. Write is author writing a paper, and cite is a paper citing another paper. So here I'm just gonna produce all the informations that we need in order to create the graph. So we are gonna have 10 authors, and the feature dimension for the authors is 8. We're gonna have 20 papers, and the feature dimension of the paper is 4. And some random links are created for each edge type. One thing that I want to show you is how we can also combine the three ways that I told you before to construct the actual object. So basically, I told you that there are these three ways, and you can combine them. So for instance, here I did it by giving an input here, a dictionary containing the information about the nodes, but then using the other strategy by with the double underscore, for instance, for the variable name, in which I give an input a dictionary. So as you can see, this is a combination of the two that I told you before, and it still works. So don't worry, you can still play quite a lot with it. Now that we have created our heterogeneous graph, let's have a look of what, if everything is correct. So basically, if I print the metadata, as I told you before, we have a list containing the node types and a list containing the edge type. They are the actual types that we imputed, so we're fine with it. The hetero class stores everything as a dictionary. So if we try to access one specific node type, we can see that what we give in output is a dictionary containing the nested dictionary, a dictionary containing all the information. So here for the author, we have specified that it has the metrics related to the nodes and their classes. And here we can see that we have this exact information stored as a dictionary. Let's suppose now that I want to get in output to retrieve all the feature metrics for all the node types, for instance. In this case, I can just have to call x, because x is the matrix representing the node types, underscore dict, and this is exactly what I get in output, another dictionary in which the k this time is the node type, and the actual value is the feature matrix. If we try to convert this data to homogeneous data, we can see that we have in output a homogeneous data type, which is a normal data type in PyTorch Geometric. However, in this case, we don't have the same feature dimensionality for the two node types. So the function is not able to produce a single metric representation. In order to do so, probably we have to expand the dimension of the lowest one in order to match the dimension of the biggest one. If we do so, then we will have an entire feature matrix for the combination of the two nodes, of the two set of node types. Some other utility is that we can again retrieve all the values for the different node types or edge types as a list, or we can actually convert everything into one single dictionary. Okay, so now that we have talked a little bit about how we can construct the data, as I told you before, we can transform the data. using the transformation package in PyTorch Geometric. In this case, I simply want to add the masks for training, validation, and test. And as we can see here, it does it for the node type author, because it is the one that has the class vectors specified. And what it outputs is this new information that we can also retrieve by treating this string as the key in our dictionary. Now let's have a little bit of a look to the heterogeneous graph neural networks and how we can convert them to heterogeneous models. So this is exactly the piece of code that I showed you before in the slide. And as I told you, so we're gonna have two, in this GNN we have two-step convolution, okay? And if I convert this GNN to a heterogeneous model, we will have now that we have, again, two-step convolutions. And for each edge type, we're going to have a specific Sage convolution. So basically, these convolutions have been replicated in order to match the number of edge types. Okay. There are also other strategies to construct the graph neural networks to heterogeneous model. In this case, for instance, we can also decide to have a specific convolution for each node type, not only for edge types. Okay, now let me see if it downloads the entire dataset or not. I hope not. And I just want you to show one last thing, which is the fact that using the very same classes for the homogeneous data, we can also perform load the nodes into batches, basically. This can be done by using the very same neighbor loader class that we can find in the homogeneous case, or we can also use its specific class, which is the heterogeneous loader. Basically, they yields the very same thing, and in this case, they are gonna simply taking parts of the subgraph, but they are basically equivalent. So nothing too special here. So this is everything from my side. There are some more stuff that you can check out on the actual Python documentation, and I kindly suggest you to start working with these heterogeneous graphs, and also to put your code online, because it's very there are very few examples on how people can write it down. So let's start using also this part of this fantastic library and share it to other developers. Thank you.
Thank you, Giovanni. Thank you for the nice presentation. Yeah, I have a question. So maybe you mentioned that, but I would like to understand it better. So potentially, I think every method in the library can be rewritten for heterogeneous graph data, right? But do you know to what extent that is done or known? Because I think maybe also different algorithms are needed for some tasks. So it's not like you can just take any algorithm that is existing for homogeneous graph and transfer it to heterogeneous.
That's a very good question. So I haven't tried of them. I mean, of course, all of them, but I have tried some, and I can say they're fairly I'm fairly confident that most of the most common type of convolutions, you can definitely convert them into heterogeneous models. Then then you also have the case in which you have similar techniques constructed for homogeneous and heterogeneous cases, like the meta path for heterogeneous data and node to back for homogeneous graphs. So it's something that it would be nice also for the people to try out and give us a feedback about this, because I actually don't know all of them, but most of them, yes.
Okay, thank you. Yeah, and also if there are no other questions, I would like to ask something else. So do you have a feeling of, so essentially if you have a graph and you add, so let's say that is homogeneous, and then you decide to add, for some reason you have another layer of data, so it becomes heterogeneous. So hopefully this will improve your prediction because you have another source of data. But it's also a computational override in some sense because your graph becomes more complex. I mean, it's just a very, very generic question, but do you have any idea if someone had a look at how much so if there is a trade-off between the amount of information and the amount of gain in terms of accuracy, for example?
That's very interesting. I am not aware of an analysis of this kind, also because for what I've seen, it's not clear how you might compare a homogeneous graph and an heterogeneous one, okay? Because you're talking about performance improve, but it's very hard to put on the same balance the techniques for heterogeneous and homogeneous. So I'm not aware of any analysis of this kind, but if anybody finds something, please drop me a message.
Okay, thank you. Thanks.
Thank you.
Are there questions from the others, or also in the chat if you prefer? No, okay, so it looks we are done. And so Giovanni, thank you again. And you will find this video in the, so I think the code is in the repository, or it will be soon, let's say, and the video will be uploaded in YouTube over the weekend. So for the ones that want to have a look in the future. So thank you again, everybody. And just a short reminder that this week, so this time we'll meet in 1 week, not in 2 weeks. Okay. So thanks, everybody, and see you next week, hopefully. Bye-bye.
Thank you.
Bye-bye.
Bye-bye.